recording. Okay. Could you just somewhere free, maybe the bottom of page 14. I was just explaining to Varad about the analogy of all these protons and neutrons. Oh, no, they're about the same size. In your nucleus. Now, what I want you to visualize is all of those protons want to repel each other. There's an electrical repulsion. Okay? And so if the neutrons weren't there and I just had 1, 2, 3, 4, 5, 6, 7, 8, 9 protons, so we are at fluorine, 9 protons, they would all go flying apart. All right? There's so much stored electrical potential that they would just burst apart going off in opposite directions. What keeps them in there is the neutrons, and there's going to be these tiny little particles. They're called gluons, and you don't need to worry about them till year 12. And they're basically transferring between protons and neutrons. So think of them as like ropes that are keeping all of these protons in. Think of the protons as like compressed springs, all right? And so if you compress all of these springs and then you tie them with little ropes so that they're stuck together, okay? Now that is a ton of potential energy. Now it's nuclear potential, not so much electrical, but nuclear, okay? And if we've got a nice ratio, we're happy because the ropes are there to keep everything bound, okay? So the strong nuclear force binds our nucleons together. If we don't have a nice ratio, if we were to remove, and it could be a proton or it could be a neutron. If we were to remove one of those, now we have an unstable ratio. So now maybe we've got too many protons, okay? And now, sometimes we see one of those, if you cut one of the ropes from my analogy, then one of those springs goes flying off and we get a lot of that energy released. Okay, so that's the best kind of analogy of what's happening in the nucleus. You've got the strong nuclear force. Now, the strong nuclear force only really acts over its neighbouring nucleon. It cannot act further than that. So really, it's acting between a proton and a neutron right next to each other. Okay? It can't go any further than its nearest neighbour. So it is a very short-range force. They've plotted it, the strength of the force. Make sure I get this shape right. Something like, hang on, I've stuffed it up. Something like that, where it really exists, that distance, that's x versus f. It really wants to exist really, really strong there, and then any part past x, it goes to 0 very quickly. It's short range, okay? Whereas your electric and your gravity does this, like that. It acts over any distance. It gets weaker the further away, but your protons are influencing all of the other protons. The strong nuclear force can only act short range to its nearest neighbour. Okay, these are very terrible graphs, but I just wanted to quickly show you that, and hopefully it explains. Again, visualize, as I said, packing billiard balls together. Below 20, you're always going to have a proton near a neutron. As you start building up this massive basketball-sized atom made of billiard balls, now you've got too many protons near each other, okay? And too many protons, occasionally, boop, something will spit out. That's why we've got to start packing in more neutrons. That's why our curve curves upwards. Where's my little graph? Where's my little graph? There he is, okay? Now, I would like you to find uranium-238 on this. So if we go up, maybe we won't be able to find it. Uranium-238 92 has 92 protons. So we're about here. Are we? Yeah. So unfortunately we don't have uranium-238, so this was a bad activity. How many neutrons are there?
146.
Thank you. And so... is it? It's off the table. Okay. How about Nah, okay. Don't worry about
It
it.
goes to 235.
Where?
On ours, the very top is uranium-235.
Did I not cut the image properly?
Well, it's got like a bunch of powerful things above.
When I took a screenshot of this, oh damn. Okay. Unfortunately, when I took a screenshot of this, I got rid of those higher up ones. What could I do? Could I go back to...
So just run some little A's and you can go from there.
No, I've also... Alright, don't worry. I was going to go on a little journey, but too bad. Let's go back down to page 14, 15. Okay. This isn't too hard to follow on. If you are unstable and you spit out a bit of energy and mass, why are you doing that? Huh? Sorry? Stop. If you are unstable and you spit out a bit of mass and energy and then you become a stable isotope, then you're happy and you'll stay there for the rest of your life. We looked at an example yesterday on our graph of just decaying straight to a square on our graph. But obviously, the further you get from that line of stability, Stanley, you can kind of tell that I'm in a bit of a foul mood.
Yeah.
Can you try and just, the further away you get, one decay is not going to get you to stability. Okay, so as soon as you need more than one decay to get to a stable isotope, it's called a decay series. The most common one is the uranium decay series. This has been happening on Earth since the Earth was made about 4 billion years ago. Now, uranium, if you look on our poster, bismuth has been highlighted as an important isotope. It's that blue box, bismuth 83. What do you notice about bismuth as you look down the column of isotopes of bismuth? What do you notice? Got one stable. Right? What else do you notice about the isotopes around bismuth?
It's where alpha decay kind of stops.
No, it doesn't stop.
Well, somewhat.
No. Look to the right of bismuth. What do you notice about all the isotopes to the right of bismuth?
Alpha.
And beta. And beta. Try again. Look to the isotopes to the right of bismuth. What do you notice? What is absent? Stable isotope. There is no stable isotope above bismuth. Everything with an atomic number greater than 83 will eventually decay. So you go, well, hey, how do we still happen to have 92 naturally occurring elements when 9 of those aren't stable? Well, they were made by a huge amount of heat and pressure and energy, and then left on their own, they are starting to decay. We are slowly going to be running out of those elements. Okay? So, if we start with uranium-238, here's the thing. It's fairly stable. You can look at the measure of its stability by a term called half-life. We're going to look at half-life next week. But it's basically the time for half of your sample to decay. So if you had a kilogram of uranium-238, in 4.5 billion years, a half of a kilogram would have decayed into thorium. So it's a very, very long half-life. But it spits out an alpha particle. Now, just be careful. This is a different graph. We've got atomic number and mass number. So this isn't the atomic number and neutron number. It's going down 4 and across 2. Thorium. If it decays to thorium, thorium is not very stable at all. It decays with a half-life of 24 days via beta, negative, transmutates to palladium, stays there for 6.7 hours, transmutates back to uranium. So isn't that strange? We've gone 3 decays and we're back to uranium, but it's a lighter isotope. Okay? So we're now down to uranium-234. Again, 250,000 years, it decays back to thorium. But again, a lighter isotope of thorium, 4 nucleons lighter. Then to radon, then radium, then to radon, then to polonium, then to lead. Now lead, everything wants to get to lead. But this lead isotope's not stable. Again, the ratio, it still has too many neutrons. Beta decay, bismuth. Beta decay, polonium. Alpha decay, beta, beta, alpha. Finally, the atom has done all of this and it's gotten down to lead 206, and that's going to be the first square where it's happy to live, okay, for the rest of its life. Most heavy isotopes are trying to get to lead, and if you pick, and as an activity, if we find lead 82, if you go up the 80 line and across 3, you would get to 82, which, you know, you can find it from bismuth. I'll quickly show you. Quickly is the optimum word here. So if you find bismuth, oh, what? I've lost bismuth. Oh well, there's bismuth there. That's our bismuth. Here's our lead. Okay. So apologies. If you pick any radioisotope in the up and left from what I've just highlighted and follow the decay mode, you will most likely get to lead. Okay? So it's all of the balls that are rolling down the hill are eventually going to sit in that well of low energy called lead. Okay? So again, I've chopped off 10 neutrons off my image, which is my own silly fault. But if you pick any decay series, alpha, remember we go down to left 2. So you could pick any, and you could make your own decay series. You would go bloop, 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 bloop. You might beta decay, down and across, boom, now you're at lead. All right, alpha, you go down 2 and across 2, you're stable. This alpha, down 2, across 2, beta, down 1, left, boom, lead. Okay, so pick any to the right of bismuth, and you will roll down and eventually become lead. So it's good to know that the Earth is slowly becoming more lead. It's slowly becoming less uranium, thorium, polonium, radon, etc., etc. In rocks, there are uranium. Uranium is a very common isotope. Don't think that it's a glowing green rod that you may have seen on the intro to The Simpsons. Uranium is a very common metal atom. As we will learn, there are some isotopes of uranium that are useful to us, but most it's in rocks, sitting there, not very active. But still, we have lumps of uranium ores. They're just like little lumps of rock. We bring them in, put a Geiger counter over them, and there is activity coming off them. They're housed in a lead-lined cabinet to prevent the radiation leaking into this classroom. What was I getting at? We've got a lot of atoms, okay? Please, I need you to be aware of chemistry. If I gave you an Avogadro's number of uranium, you would have about 238 grams. So if I brought a rock into this classroom that was 238 grams, you have Avogadro's number of atoms, okay? What's that? 10 to the 23.
6.00022
times 10 to the 23. So you got 10 to the 23 atoms. So don't be surprised that you can have an activity of, you know, thousands of decays per second, because you have a ton of atoms sitting there. Okay? So that activity can last literally for billions of years. Have a think. If you've got 10 to the 23, and every second 10 to the 3 go, there's 86,000 seconds in a year. So that's, now you're up to 10 to the 5. Times that by 10 to the 9. In a billion years, 10 to the 14. But you've got 10 to the 23. Okay, so you need to be able to appreciate orders of magnitude. We have plenty of atoms. Okay, and that's why activity can go for a very long time. Just on rocks. There are lots of uranium in rocks. There is lots of thorium. There's lots of radium. Certain types of granite in America at least, and certain types of granite around the world, have radium in them, which occasionally over time alpha decays to radon. Radon is an inert heavy gas, yeah, group 8 elements, yes? Complete outer shell, noble gas. There is an issue with this decay series. People that build their houses with granite, and in America they tend to build basements. We don't tend to have basements in Australia. Too hot, I don't know. But in America, basements, granite walls, granite retaining walls, granite ceilings. The radon, when it is made by the transmutation alpha decay of radium, it actually just leaks into the basement. And there has been accounts of people going down into their basement to, I don't know, pick up a book or something, and then they just and they fall over dead because the basement's been filling up with radon gas, and because it's heavy, right, it displaces all the air, and so you're walking down into this dense gas and you don't know it because it's inert, colourless, odourless, doesn't smell, can't taste it, and you go in and get your favourite physics book from your basement shelf, and then all of a sudden, you know, you're dead. Okay, so you can get, in America, if you have basements, you can not only, like smoke detectors, they're important Australia legislation, they've got to be installed. In America, radon detectors can also be purchased, and you place it, well, smoke rises, right? So we put our smoke detectors on the ceiling, you put your radon detector in the corner, in the bottom of the wall. And it's, I don't know, don't ask me how it detects radon because it's not chemically reactive, but beep, 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 you know, if your room's filling up with radon gas. They get a big straw. How would you get water out of a flooded basement? A bucket? Okay, well then you would get a bucket and you'd throw the bucket of radon gas out and it would roll downhill. Okay, so yeah, I don't know, suck it out with a hose. Alright. This is just tedious busy work now in the last 6 minutes. Could you please write every single one of these? Yes. Tedious busy work. Quick, just come and copy Jamon's work. No, just read your own work, Matty.
9234. You just said it was tedious.
It's tedious because you don't have to think. You've got your uranium-238, 92. Thorium-234, 90, plus alpha. It's all there. You just grab the information off
It's just an alpha, isn't it? Or?
You know we're doing it on the page.
Oh no, plus energy.
Write all the nuclear equations for each decay to uranium-238 to lead-206. You don't have to add the times. Don't worry about the times. Just the decay mode. Well, there would be beta negatives because if you're making a proton. Yeah. You're making a proton, you've got to spit out a negative charge to conserve charge. So they are all beta negatives. Matty, did you manage? I know you were trying to talk to me. What can we get? How high up can we get? Like, is there? You said something.
Like when it goes up to uranium-235.
So we
can't
can start there.
Yeah, we can.
Okay, so we wouldn't get the first two. All right.
Yeah.
In future years, I'll probably do my homework and find it, and then we can write it. Or you can do it for me. If you can find uranium-234 on the poster, and then you should be able to track the decay sequence. Yes. Decay series.
Okay.
You wrote that arrow there.
I did not. It's up on the board.
No, that's just, it's showing, because there's no room, it's saying that palladium decays via beta to uranium. Here, let me get the ball rolling. Uranium-238, 92, goes to thorium-234, 2, 3, 4. 88 plus alpha. Oh, that should be 90, sorry. Try that again.
Thorium 230.
Then thorium, so now you do a brand new line, yep. Decays to palladium 91, 2, 3, 4, by spitting out a beta negative particle and an antineutrino.
Also in the anti-neutrino reactions as well. There's always energy in there. Always energy.
Always energy, yes.
Always energy.
Always.
Always energy.
You have to write energy out there.
226. Yes. You have to waste your time writing out an extra.
No, antineutrino for beta negative and a neutrino for beta positive.
There is no beta positive.
Yeah.
Where's the beta positive? Where's the beta positive?
There is no beta positive.
I'm just thinking.
Why are you trying to scare me?
Exactly right.
Alright, well, it's working.
That's radon.
Okay. And then we can do another alpha decay, 92, 2, 3, 4.
That is a really damning alpha.
What have we got into? Thorium.
218. Wait, what? Did I miss like 5? Jesus. Oh god.
Oh no, hang on. So now think of the early 1900s physicists that gets a sample of a uranium ore. They don't know what the hell's going on because they're getting so many different particles being emitted with so many different energies. They're getting traces of thorium and palladium. So this was the issue. They thought that their sample was contaminated. What they didn't know was that they were literally, it was spitting out bits of energy and transmutating into different elements. So this was a really nasty puzzle that confused scientists for decades until somebody was able to try and explain what the hell was going on. Yes?
I don't know if anyone's asked this yet, but why don't people just transmutate into gold from like something?
They've tried alchemy. So you can. Not well. That's how they made plutonium. Wonderful story, many books. Midway through the war effort, have you finished your decay series?
I'm at uranium.
Well,
Which one?
tough. Mr. Murray story time.
Really?
Not until you finish
Only that far?
your decay series.
Better if I said the first one.
Jimon.
Is writing plus energy is that the same as plus like
Lead to 10.
No gamma there. Actually, they don't always go metastable. So sometimes some decay products will be metastable, some will still be stable.
So, if it isn't energy on the left beta positive? No.
No. So in all of this, matter is being converted into energy.
Yeah.
Okay. So what you find, and this is going to, hang on just a second, this is going to be our week 10 content, but if we weighed the mass of the, try that again.
is the edge one 20682?
What?
Is the last one 206?
82, that's lead 206. Who was asking about energy and what side it's on? Matt or Jamon? Huh?
And me.
Okay. So, in all of these, energy is released. If we weighed the mass of this atom, it's heavy. If we weighed the mass of the products, it's actually lighter. There is missing mass. And Einstein said that the missing mass has been converted into energy, E equals mc squared. So literally, the mass defect, it has a special name, the mass defect has been converted into energy. And you can literally calculate it because we have isotope masses in our lists.
So when would energy be on the? You said something about energy.
Well, that would be if we wanted to go backwards. Look at the projector. if you wanted to turn lead-206 into polonium-210, you would have to put that energy back in.
So just punch it really hard.
Well, that's what they're doing at CERN. They're just punching stuff really hard and hoping that they make stuff.
Come on, so close.
They're turning energy into mass. So yes, midway through the World War II war effort, they're trying to enrich uranium to make a bomb. They realised that if they fired neutrons at uranium-92 234, it actually transmutates via beta across. Now, if we look here, uranium-234 wants to decay to thorium, but if you fire it with neutrons, it can capture a neutron and now become unstable. Too many neutrons, it actually beta decays across into this new unseen territory called the transuranic elements. Never before 1943 was there an atom on Earth that had 93 protons. And by beta decay, it transmutated into Neptune with an average half-life of about 4 hours, which is good. And then it would transmutate again to 94, element number 94. They actually called it element X because, you know, in the war effort, everything was confidential and they didn't want people knowing. But that became plutonium. And plutonium, it was uranium-238 that they did that to.
Oh.
And then neutron, uranium-239, transmutates, becomes plutonium-239. And that goes bang a lot better than uranium-235, which also goes bang. But not as bang. So halfway through that effort, they focused all their attention on making plutonium. So the two bombs that were dropped, one was uranium, one was plutonium. Yes, Scotty, yes.
Yep.
What did?
Where was I going to
It
fit
did. If it didn't, you made a mistake.
Fit it all in there. Cheers,
So
sir.
this is the crazy thing. You stop at uranium twice and thorium, then you stop at polonium 3 times. But every time you're getting lighter and lighter and lighter. Energy's getting released. Rookie error.
Why can't we just go?
Alright, yes, what is it?
End of the lesson.
We probably won't mark it down. Nuclear equations are generally like matter. See you later. Have a good weekend. Alright, have a good weekend. See you all tomorrow. See you all Monday. Now I screen captured that, but it's not really the greatest lesson, is it? Oh well.